Hello, everyone. In this section, we will introduce the concept of a small signal amplifier using bipolar junction transistors, or BJTs. The circuit shown here is a typical basic form of a BJT voltage amplifier. The input voltage signal is applied at the base terminal and is denoted as VBE. The output voltage signal is taken at the collector terminal and is denoted as VO. Since the emitter terminal is grounded, the output voltage VO is the same as VCE. Therefore, VCE equals VO, and it is equal to VCC minus IC times RC. The BJT collector current IC is equal to IS multiplied by the exponential of VBE over VT. Here, the ratio VBE over VT is inside the exponential term. By substituting this current equation into the previous voltage equation, we can obtain the relationship between the output voltage VO and the input voltage VBE. This relationship is called the transfer characteristic curve. According to the IC current equation, the behavior is similar to the forward bias equation of a PN junction. In other words, when the VBE bias is below about 0.5 volts, IC is very small and can be approximated as 0 amps. Therefore, VO is approximately equal to VCC. At this point, because the collector current is almost zero, the BJT can be treated as operating in cutoff mode, as shown in the transfer characteristic curve on the right. When VBE becomes larger than about 0.5 volts, the collector current IC rises significantly. This increases the voltage drop across RC, so VCE, which is also the output voltage VO, begins to decrease. As long as VCE remains greater than about 0.3 volts, the BJT operates in active mode. The corresponding part of the transfer characteristic curve is shown in the diagram. However, as VBE continues to increase, IC also keeps increasing, and VCE gradually falls below 0.3 volts. At this point, the BJT enters saturation mode. In saturation mode, the dependence of IC on VBE becomes much weaker, so the VCE versus VBE curve becomes saturated, as shown in the diagram. Therefore, when the BJT operates in saturation mode, the saturation collector current can be calculated as IC sat equals the quantity VCC minus VCE sat divided by RC. Here, VCE sat can be approximated as 0.2 volts, as introduced in the previous section. The voltage gain of a voltage amplifier is the output signal divided by the input signal. For small signal analysis, this means the output variation VO divided by the input variation VBE. Equivalently, it is the derivative of the total output voltage VCE with respect to the input voltage VBE. This derivative is the slope of the transfer characteristic curve, and it represents the voltage gain of the amplifier. From the diagram, we can see that a high gain is obtained only when the BJT operates in active mode. If the DC bias point is not in active mode, the circuit cannot reach its maximum gain and may even fail to amplify the signal. After introducing this BJT amplifier by using the transfer characteristic curve, we now calculate its voltage gain from the mathematical equations. As mentioned earlier, the output voltage VCE equals VO, and it is VCC minus IC times RC. The collector current IC is IS multiplied by the exponential of VBE over VT. Under the conditions VBE greater than 0.5 volts and VCE greater than 0.3 volts, the BJT operates in active mode. Therefore, VCE equals VO, which equals VCC minus IS multiplied by the exponential of VBE over VT, multiplied by RC. The total input signal VBE is the sum of the DC bias voltage, capital VBE, and the AC small signal voltage, lowercase vbe. Substituting this into the output equation gives the total output voltage, VO equals VCE equals VCC minus IS, times the exponential of the quantity capital VBE plus lowercase vbe divided by VT, all multiplied by RC. Here, the entire sum capital VBE plus lowercase vbe is inside the exponential term and divided by VT. Because the voltage inside the exponential term is a sum, the exponential can be separated into two factors. The exponential of capital VBE plus lowercase vbe over VT becomes the exponential of capital VBE over VT, multiplied by the exponential of lowercase vbe over VT. Therefore, the output voltage can be written as VCC minus IS times the exponential of the DC VBE over VT times RC times the exponential of the AC VBE over VT. Since the DC collector current IC equals IS times the exponential of capital VBE over VT, this becomes VCC minus IC times RC times the exponential of lowercase VBE over VT. When the small signal ratio, lowercase VBE divided by the thermal voltage VT, is much smaller than 1, the exponential of VBE over VT can be approximated as 1 plus VBE over VT. Here, VBE over VT is the quantity inside the exponential function. Therefore, the total output voltage becomes VCC minus IC times RC multiplied by the quantity 1 plus VBE over VT. Expanding the bracket gives VCC minus IC times RC minus IC over VT times VBE times RC. This expression contains two parts. The DC output voltage, capital VO, equals VCC minus IC times RC, and the AC small signal output voltage, lowercase VO, equals negative IC over VT multiplied by VBE and RC. Finally, the voltage gain AV is the AC output signal VO divided by the AC input signal VBE. Therefore, AV equals negative IC over VT multiplied by RC. Since the gain is negative, the output signal is 180 degrees out of phase with the input signal. This result is consistent with the earlier transfer curve interpretation. The voltage gain of the amplifier is the output signal divided by the input signal, or the small signal output variation VO divided by the small signal input variation VBE. This is also the derivative of the total output voltage VCE with respect to the total input voltage VBE. Therefore, at the DC operating point capital VBE, we can differentiate the VCE equation with respect to VBE. This gives the voltage gain as negative IS over VT multiplied by the exponential of VBE over VT and multiplied by RC. Since the DC collector current IC equals IS times the exponential of VBE over VT, the gain becomes negative IC over VT times RC. This is the same result as the previous derivation. Next, we use graphical analysis to study this BJT amplifier circuit. In the previous sections, we introduced the BJT current voltage characteristics as shown on the right. The collector current IC changes with VBE, and it is ideally insensitive to VCE. However, due to the early effect, IC slightly increases as VCE increases. In addition, if VCE becomes smaller than about 0.3 volts, the BJT enters saturation mode and IC drops significantly. This is the IC versus VCE relationship from the viewpoint of the BJT itself. Now let us look at the circuit from the viewpoint of the resistor RC. We have VCE equals VCC minus IC times RC. Rearranging this equation gives IC equals VCC divided by RC minus VCE divided by RC. This is a straight line equation with a slope of negative 1 over RC. When VCE is 0 volts, the line intersects the IC axis at VCC over RC. When IC is 0 amps, VCE equals VCC, so the line intersects the VCE axis at VCC. We then draw this straight line on the IC versus VCE plot. The red straight line in the IC versus VCE characteristic plot is called the load line. We can see that different DC input biases, capital VBE, lead to different intersection points with the load line. For example, when the DC input voltage is VBE3, the intersection with the red load line is the Q point. This Q point is the DC operating point of the amplifier, giving the DC voltage VCE3 and the DC current IC3. When an AC input signal VBE is applied, the total VBE changes. If the small signal input VBE from the IC versus VCE characteristic plot, we can also see that the output voltage VCE cannot exceed VCC. Therefore, when a negative VBE signal at the Q point makes VCE rise, the upper limit is VCC. The range from the DC bias point VCE3 to the limit VCC is called the headroom. It represents the upper output swing allowed by this circuit. When VCE reaches VCC, IC becomes 0 amps, meaning that the BJT is in cutoff mode. Conversely, when a positive VBE signal is applied at the Q point, the output voltage VCE decreases. If VCE falls to about 0.3 volts or below, the BJT moves from active mode into saturation mode. As introduced earlier, When a BJT operates in saturation mode, its gain becomes very low and it may no longer amplify the signal effectively. Therefore, the range from the DC bias point VCE3 down to the active mode boundary at about 0.3 volts is called the leg room. It represents the lower output swing allowed by this circuit. The slope of the red load line is -1 over RC. When the load resistance RC is low, such as RCA, the magnitude of the load line slope is larger, so the load line becomes steeper. For a given change in the input signal VBE, for example from VBE1 to VBE3, the change in the output voltage VCE becomes smaller. Therefore, the voltage gain is lower. In addition, the operating point QA has a larger VCEA, which reduces the headroom. This means that the negative swing of the small input signal VBE cannot be too large. Similarly, when the load resistance RC is high, such as RCB, the load line becomes flatter. For the same change in VBE, the output voltage VCE changes more, so the voltage gain increases. However, the operating point QB has a smaller VCEB, which reduces the leg room. This means that the positive swing of the small input signal VBE cannot be too large. Therefore, in amplifier design, the choice of RC must consider the trade-off among voltage gain, headroom, and leg room. This concludes the introduction to the concept of small signal amplifiers using bipolar junction transistors. Please look forward to the next lesson. See you next time. Bye-bye.